I often learn things here in a short conversation that would take me weeks, months, or years to gain that same experience on my own.
All right, that's the timer going off telling me it's time to start. So how's everyone doing today? Had a good CppCon so far? It's coming to an end. I know it's been a long week. If you are like in that back section, I will let you know there is a lot of code on these slides. No slide has more than 25 lines of code, but that's still actually quite a lot. Some of it's pretty small, and you may have trouble reading it. If you want to move to the front section, it'll be a lot easier. Alternatively, if you can't move up for one reason or another, I did post the slides on the Discord channel, on the CppCon Discord, the Discord channel for this talk. Also, feel free to leave comments, heckles, whatever there. Code that shows me I'm wrong. All of those things are fine. Anyway, I'm going to dive right in. I have quite a lot to talk about, and I do talk a little fast, so if you are lost, like, throw both hands up and say I'm completely lost. I'm going to try and take questions at the end, though, like actual questions at the end. So if just some signal somehow that you're completely lost and I need to slow down. Also, if you're watching on YouTube, you can watch it in slower speed because I do talk very quickly, and I'm sorry about that. I get very excited. This is some really cool stuff. I've been hyping it up all week, and I'm actually really excited to talk about it. So let's dive right in. For those of you who don't know me, I have been involved in the C++ committee for quite a while now, 8 years. I am currently, so I've worked on MD-SPAN, I've worked on atomic refs, did execution, quite a few other things in the standard, a lot of smaller features also. I am currently the chair of Study Group 9 of the C++ committee. Study Group 9 is the group that's responsible for the design and evolution of ranges. So this talk is a little on topic. That doesn't mean I know more about ranges than everyone on the committee. In fact, it specifically means I do not. It means that I'm in charge of getting the people who know more than me about ranges to agree with each other. And that's quite a challenge. It also doesn't mean I'm a ranges super fan. Like, I am a big fan of using the right tool for the job in the right situation, and very many times that's not ranges. And I think this presentation may convince you of some more times that it's not the right tool for the job. So I'm very openly critical of like certain parts of ranges, and that's the point, right? That's the point. We need to evolve and become better with what we have in the library. It does mean I get to play a lot with C++, a lot more than most people. I get to justify playing with C++ 26 features long before they're coming out because this is something that I actually get to work on with the committee. And this talk is kind of mostly in the spirit of playing, right? It's like, hey, this kind of seems to work pretty well. What could we do with this in the standard? What would it look like? So I was told at the speakers banquet and then also at the community dinner that summary slides are good. So here's a summary slide. I don't do a very good job at summary slides, but let's go. We are going to start by describing a major flaw in the design of ranges. Like all things C++, it has this barely pronounceable name called TPOIASI. Just like Spine. Can anyone off the top of their head know what TPOIASI is? Okay, fewer people read that blog post than I thought. Wow, not even some of my standards colleagues. So yeah, we'll get into that, and then we'll get to the bottom of what's causing the problem. We're gonna do this in the DAISY way. If you've seen my talks before, you know I love to dive way down deep into code, into the very base layer, the very fundamental piece of things. We're going to use real code. It is going to come from the standard library. I'm going to put standard library code that I copied and pasted onto these slides. And if you think I'm crazy, that's probably because I am. We're going to talk about a solution that turns ranges kind of inside out. Hopefully by the end of the talk, you'll really understand what that means. And then we're going to implement some of these live. So I'm excited to do that with you all, and I'll call out and say, hey, can anyone figure out what goes on this line? And then we'll talk briefly about what this could mean for the future of C++ and how this maybe fits into the kind of vague picture I have for ranges that doesn't really matter because I'm not the person who decides the direction, it's the people in the room with me. But anyway, here we go. TPOIASI, I guess is how you pronounce this. It's the terrible problem of incrementing a smart iterator. This was from a blog post in 2019 by John Picara, who's one of the cool people in the C++ community that I don't think I've ever met in person. If I have, then please tell me. I'm sorry, John. And he said it's not a showstopper for ranges, but it can be a real issue, and in all cases, it's good to be aware of it. So hopefully you will understand what TPOIASI is by the end of this talk. And let's illustrate it. Let's start by illustrating this. So again, lots of code in these slides. This is kind of a very, very fundamental, simple use case of ranges, right? Transform and filter are probably two of the most fundamental operations in all of ranges, and a lot of different operations can be expressed as filter or as transform. And if we do this with C++ 2023, we have this print line, so we can pretend we're writing Python, and take a vector, pipe it into a transform where we're doubling things, and then pipe it into a filter where we're filtering out things that aren't equal to 0 mod 4. And you can see if you were to walk through this in your brain, right? 1 gets multiplied by 2 is not equal to mod 4, so it doesn't get passed through. 2 multiplied by 2 is equal to 0 mod 4, so we get 4 coming out, and then 3, and then 4 times 2 is 8. Mod 4 is 0, so you get the idea, right? This is how ranges work. Let's do this a little differently, and let's print out, do our classic printf debugging, or print line debugging now that we have print line, where we print out in each one of these functions how many times these things are being called. So how many times do we think we're going to see transform being called, and how many times do we think we're going to see filter being called? Anyone want to guess? So you would hope 5 and 5, right? You would definitely hope 5 and 5. Unfortunately, it's 5 and 7, or 7 and 5. I don't forget which order I said those things in. But anyway, weird things going on here, right? Transform of 2 is getting called twice. I'm going to go through one way, and transform of 4 is being called twice, right? I'm going to go through one way of understanding why that's happening. If you want another great way of understanding why that's happening, take a look at Nico's talk from earlier this week. Nico Jasudis. I don't actually know how to pronounce his last name correctly, but I think I got it. Nico gave a talk on taming the filter view, where he goes through this and a bunch of other problems with the filter view. He does an excellent job of explaining it. He's an actual educator, so he knows what he's doing, and I'm just kind of doing this for fun. But I'm going to go through it and explain it the way that I understand it. And hopefully you can follow that. So is filter broken, right, is the question. So we're going to go into real standard library code. I'm actually going to put some copy and pasted code on the screen, and then I'm going to actually kind of walk through what my brain does when I'm reading this code and what my brain kind of ignores. I think this is actually a really valuable skill. I think it's something to have in your toolbox. The standard library is not a tutorial. The standard library is not really meant to be read by normal programmers, but you still can learn something from it, right? You can click through in your IDE, you can go to the definition, you can read it a little bit, and sometimes it's not going to be helpful. I'll be honest, sometimes there's so much going on in the standard library that it's really not helpful. Std variant and std tuple, very hard to read code. But sometimes it is going to help you, and it's good to have in your toolbox that, hey, this is not unreadable code, this is not a black box. It's code like any other code. It just has a lot more complicated requirements on it. So let's start by looking at transform view. This is what libc++ does with transform view. There's quite a lot going on here. And so when I start diving in and looking at this, I see that, okay, there's a difference between versions, so I don't really care about that for understanding what I'm trying to understand, right? We're trying to understand what's happening in the code that we just looked at, right? So we don't really care about the difference between movable and copyable functions. We don't care about API. We don't care about the constraints on transform view. We know that it inherits from view interface because the standard says it does, but like that's not all that important for this. So like my brain is actually taking all this stuff out, and actually on this slide I didn't even take quite as much out. I could have taken this out. I probably could have also taken this out, right? And seeing this, and this is actually like closer to readable code. I know there's underscores in it. Don't freak out. Underscores are awesome, and if you look at them enough, they give you power. I promise. You really do. Like if you've never written standard library code, it feels powerful. So here's the first part of this template definition. We have nested types for an iterator. We have this template bool on the iterator that we don't really know what's going on with that, and there's no real way to figure that out from like looking at this immediately, just this part. So what we're kind of going to do mentally is we're just going to push onto the stack like, hey, this is something I didn't quite understand. And if it ends up being important later, I'll pop it back off and try and figure it out. And if not, I'm just going to push it there for a second and say, okay, maybe it'll become clear, maybe it won't, right? We have this like no unique address macro. Almost all of the macros in standard library code you can just completely ignore immediately, unless you really want to know something very specific. So we have these data members, func and base, right? So right here, we can already see that like we're holding the underlying view, right? We're wrapping one view in another view, right? And that's how ranges compose with each other. We have this movable box that does something. It's not all that important. We can push it onto the stack and find out if it's something that we care about later. But for now, we're kind of looking at the code like this. We're thinking like this, right? We're looking at the two data members. It's the transform function and the underlying view, right? And so then we can look down at the begin, right? At transform view begin, right? We have a whole bunch of stuff we can pull out that is not all that important. And we end up with this, looks like begin without const is returning iterator false, and begin with const is returning iterator true. So it looks like the implementers are just using this template parameter to implement the const iterator and the non-const iterator in the same template. We don't care, right? We're trying to understand what this weird code that we had where transform's getting called a whole bunch of times is, so we can pretty much ignore this template parameter for now. We can think about it, either the const or non-const one should be fine, right? Let's look at the iterator. We again have these branches. I'm not going to keep copy pasting directly from the library. I'm going to actually just skip to the cutout view at some point, but I'm going to do it a few more times to just give you some idea of like what my brain's doing. Like we've already figured out that we don't need this, right? We've already figured out that we don't need the const. We've already figured out that we don't need to understand these requirements, and that like this difference doesn't matter to us. Iterator category is something that is not relevant to what we're doing, and if we don't understand that it's not relevant, we can push it onto the stack of things we don't understand and find out if they're important later, right? So we end up with this. Like this looks like code that you would normally write, almost. Like, I mean, maybe you're not used to writing concepts yet, so maybe you don't know what all of these are, but you end up with something that looks almost like this, right? In your brain. And then we have these nested member types, right, where we have the actual view that the iterator is for, and then we have the view underlying that view, right? So this is the thing that the filter view is wrapping. We carry a pointer back to the transform view, and we hold an iterator to the underlying view of the transform view. So in the case of our example, right, going back, in the case of our example, we are holding, actually, let me go back. Oops, that is not the key I meant to hit. In the case of our example, right, this transform view is wrapping the vector. So this is the iterator to vector there, right? that is being stored here in the transform view, right? So what is transform views plus plus doing? Well, it's just incrementing the other underlying iterator. That's very straightforward, right? It's exactly what you'd expect. We are incrementing the iterator over the vector when we increment the transform iterator because it's a one-to-one operation. It's very straightforward. Here I have more cruft that I included for some reason, but this is like your brain removing it. And we look at the dereference operator. Here's the dereference operator of the transform view iterator, right? And here we finally understand what transform view is doing and how it's doing it, right? It is invoking the function from the view with the dereference of the underlying iterator, right? So this is the dereference of the iterator to the vector that we piped into this, right? And we are invoking the function. This star here has to do with that whole movable box thing. It's not a really big deal, right? But this is pretty readable code, right? Does anyone who thinks this is reasonably readable code? Okay, good. So I hope that we can like start to get over like, I'm not saying that anyone in this room necessarily has a phobia of reading standard library code, but I have heard many times that the standard library is just not readable. And I think there's actually quite a bit of it that is. There's quite a bit of it that isn't, don't get me wrong. So transform view is doing exactly what we expected, right? Like this is pretty close to what we expected. So let's look at filter view. I am gonna leave out something having to do with the cache. If you really wanna understand how convoluted and messed up that is, go watch Nico's talk that I mentioned earlier. But we have something similar here, right? We have this indirect unary and predicate of the iterator of the underlying view. And if we don't know what that means, we can push that on the stack also, right? Like that's not all that important here. Oh, I have a side-scrolling code sample. This is the problem with HTML slides sometimes, but you get the idea here, right? Like maybe that's a piece that we could ignore, maybe it's a piece that we can't. In the filter view, we have the same thing, right? We have this underlying view that's wrapped and it gets stored as a data member of the filter view. So in our example way back there, this is the actual transform view, right? The transform view object is being stored inside of the filter view object, right? We are composing kind of from right to left in this pipeline, right? We have another movable box that we've already figured out doesn't do much important for what we're trying to understand. And this is the pred is the predicate. It's what we call the function when the function returns a bool. So here's same kind of layout, right, as transform view. There's nothing here that's really tells us what's going on. We do have an iterator, so we probably should go look at the iterator. Here's the forward declaration of it. libc++ likes to implement nested types in out of line. So usually they get declared here and then they're like somewhere further down the file. So we go scan down the file, we find this. We have the same indirect unary predicate that doesn't really matter that much. I just couldn't think of like what to put there as a replacement for what my brain does. My brain's mostly ignoring it, right? And here, again, we're holding the underlying iterator, right? The implementers even did us a favor and named it the same thing, right, as in the other view. And this is the iterator, so that we are holding a copy of an iterator to the transform view inside of our filter view iterator. And we're holding a pointer back to the filter view itself, right? So that we can get the predicate out of it. We scan down a little bit and we look at operator ++. And the implementers here have done something pretty clever that doesn't give us a whole lot of intuition for what's going on. And so we can actually scan down a little bit further, at least for the purposes of this presentation, and look at operator --. Operator ---- has an implementation that is a little bit more straightforward to read. And it's, for all purposes, I can figure out identical to operator ++, except for it does ---- instead of ++. But this is a little bit more straightforward to read, even though the clever call to find if, I think, ranges find if is pretty cute. But here you can see we're incrementing the other underlying iterator while the invoke of the predicate is not true, right? And that's the semantics of a filter view. That's what we intuitively think a filter view does, right? But there's something really interesting here, right? Inside of this invoke, we are dereferencing the iterator to the transform view. Does everyone remember what the dereference of the iterator to the transform view does? Yeah, it transforms. It invokes the function. So inside of operator ++, we are invoking a transform function, right? Which makes sense. Intuitively, if you're wrapping a transform view, you have to transform it anytime you need the value, and if you need to filter something, you need the value, right? The problem is we are also dereferencing the transform view in operator star. And that's a problem. That's where we got these two invocations, right? That's actually not what we kind of had expected, per se. So just to summarize again, right? Inside of filter view ++, we are dereferencing the transform view iterator. And that dereference is calling the function, right? It's calling the transform function. But then also in filter views dereference, we are dereferencing transform view. And that's also calling the function. Did I lose you, Dave?
Your simplified operator ++ can walk off the end. The more complicated one,
Yeah, the comment was that the simplified operator ++ can walk off the end. I would assume that the simplified operator - can also walk off the beginning. And that may be true. You may be correct. Anyway, the point is that ranges find if is doing something very similar to this, right? And so that may be the case. I'd have to think. I'm kind of in a flow right now. But good point. Okay, deep breath. We've already seen, we've by looking at the standard library, kind of developed some intuition for why functions that filter positive are getting transformed twice, or why elements that filter positive are getting transformed twice when we compose this way. Everyone take a deep breath. We're going to stop looking at standard library code for a little bit. Is that okay? 37 minutes left. All right. We might actually get through quite a lot of this. I'm pretty excited. Does anyone feel like they're completely lost at this point? Awesome. I'm pretty excited. Okay. So let's take a step back and ask, is filter view broken here? Right? Is this something that we didn't think people would mess up when we put it into the standard? Well, first of all, it's not just filter view, right? Anything that dereferences the underlying iterator somewhere other than operator star is going to have this problem. It's going to call an extra transform, right? So drop while, for instance. Anyone have a guess as to where drop while is dereferencing the underlying iterator other than operator star? Nico said it. No, it's actually in begin. Drop while begin. This next one, I will buy someone dinner if they can come up with it. Not even kidding. Yeah, that's exactly right. It's in sentinel : operator equals. You know, chunk by also, I think chunk by does it in ++. It does it in a couple places, but like these are examples. And these extra calls are not intuitive. They're not obvious, right? It's not obvious why this is happening until you look at the code and say, oh, okay, that makes sense. Like it needed the value multiple times, right? And maybe you could figure out that it needed the value multiple times from first principles. I certainly didn't occur to me until I started to look at the code and see what was actually happening. Anything that dereferences elements more than once also is going to have this problem. So like slide, for instance, or standard algorithms like set difference or is permutation or std sort, right? These are all going to have the problem also. Interesting thing to ask here is this a problem of people not fundamentally understanding laziness? Does the programmer not fundamentally understand laziness if they're seeing these extra invocations? So let's talk about the vector piped into transform, piped into slide, right? So for those of you that don't know what slide does, I stuck it in here. It goes through, so slide of 3 will pass on like this chunk, and then this chunk, and then this chunk, right? So slide of 3 piped into transform is gonna have this chunk times 2, and then this chunk times 2, and then this chunk times 2. Transform piped into slide 3, right? And we get exactly what we'd expect, right? Also, like, how about a hand for the people who standardized print line in 23 and the range adapters? Like, this just works. This is the kind of thing that gets me excited, that really maybe C++ standardization is worth the amount of time and energy and blood and sweat and tears that we put into it, because this is like exactly the problem that everyone has with C++. Okay, sorry, soapbox. Anyway, getting off my soapbox. But yeah, how many times do we think f of 3 is evaluated? Anyone want to call it out? 3. Yes. We would hope it's evaluated 3 times. It is, right? It's evaluated 3 times. And this is not all that counterintuitive, unless you think that transform is eager, right? Unless you think that this is looping over the vector, calling transform, and then looping over the vector, calling slide, right? If you're thinking that way, then this is unintuitive. You would think that f of 3 would be called once, right? And there are absolutely people in your company who think that. Does anyone think there's not someone in their company who thinks that? Awesome. We are all living in reality. Okay, cool. So if f is expensive, and you see this in code review, the author probably didn't understand that transform was lazy, right? In other words, they probably didn't understand that f isn't evaluated until it's needed. We can argue offline in another context in the YouTube comments about whether or not that's a reason to disallow ranges in a large-scale context. I think that to some extent you have to trust programmers to make their own mistakes, but also that's going to cost your bottom line at some point, right? Like evaluating extra functions that are expensive is going to cost your company money. So there is a lot to be said for trusting programmers and not babying them. There is also a lot to be said for making money, or so I'm told. So that's another discussion to have. That is not this talk. My question I'd like to pose to you here is transform pipe into filter the same flavor of problem? Is the surprise here because someone doesn't understand laziness? So like, this is the same example we had earlier, just so that I couldn't go back. I'm doing it differently because I don't know, I want to confuse people, I guess. But we're counting the number of times f of 2 is invoked, and we're printing it out here, right? And we get 2, just like we had before, right? F of 2 is getting invoked twice. Here's my question. When is the result of f of 2 needed? Like, what is the latest point when the result of f of 2 is needed? And it really depends on how lazy you are, right? There is the latest possible time, like, well, technically, the latest possible time you need to invoke f of 2 is right before you print it, right? If we treat this as a black box, if we treat ranges as some magic that somehow figures out what the developer intends to do and knows how it's going to be used in the future, then to evaluate this statement, print line here, right? The latest possible time is right before print is about to print it. Is that when f of 2 is getting invoked? Is that the first time f of 2 is getting invoked? No, right? The surprise here actually comes from eagerly evaluating operator plus plus before we know when or if we're going to use it. And that was, I think, this is a really important insight. This is the climax of the presentation, I think. Like, laziness is not the fundamental problem here. It's picking a particular point on the continuum of lazy programming model choices that is causing this problem. And we're separating things into customization points that don't quite fit our intuition as to how things should work. And so I would argue, you're welcome to argue with me in the YouTube comments, on Reddit, on Twitter, whatever, but I would argue that this is a different flavor of surprise than the laziness on the previous slide. And I think because of that, I don't think that just teaching people how laziness works and how to use lazy programming models and how to use functional programming models is going to solve this problem. I think we actually need to think deeply about other designs potentially. So the question is, what if we could wait until we know what we're going to do with the result of f of 2 before we call it? I'm going to take a look at one approach to that, and we're going to implement it in these slides, not actually live because I don't like typing live, but kind of live. And there are a couple other approaches. Like there's probably a way that we could look at the current model we have and add a customization point that can be used when the underlying code knows that it's going to increment and dereference. Maybe. I don't know. I haven't looked at that part. I'm sharing something else that I think is another way of looking at this problem. So let's talk about pull versus push programming models. And I often see people mix up pull versus push with lazy versus eager. Those are two different axes. You can have all four combinations of those things. You can have eager pull models, you can have lazy pull models, you can have eager push models, and you can have lazy push models. Making a slide of all of those in a box would have been a really cool slide, but I didn't do that. So, anyway, I'm gonna run out of time anyway. So let's look at this pipeline expression, okay? I'm gonna stop using the vector and I'm gonna start using iota. Iota does the same thing in this context. For those of you who haven't seen an iota view or an iota range before, it generates numbers starting at this one and ending before this one. And we called that iota because we're really good at naming things on the committee. And everyone knows exactly what iota means in this context. And so this does the same thing as the vector that I was showing in the earlier examples. Anyway, so here we have iota, pipe into transform, pipe into filter, pipe into two vector, right? This is the thing that we were talking about earlier that had this TPOIASI problem. And one way to look at this in kind of a pseudocode hand-wavy sense, this is, I promise, the only pseudocode in this slide. Everything else is real in this slide, in this presentation. Everything else is real code. We're vaguely speaking, we are thinking about the wrapping happening from right to left, right? So transform wraps an iota view and transforms it with a function. Filter then wraps that result with a filter. And then two vector wraps that result, right? So we are kind of composing right to left. And the object that we're getting out, that's the outermost thing, is an instance of two vector, or an instance of two vector composed or whatever, right? Like, there's a number of ways to implement this, but in other words, each subsequent view wraps its input. I think I'll probably will mess up and say input iterator or input range a few times. I don't mean the literal stood input range in that context. I mean something coming from the left side of this pipeline, something that is wrapped input-wise. What if we look at this a different way, right? What if instead we could have each view wrap its output? So we compose in the other direction. So we have a filter of a two vector of G, right? So this is like saying anything I get, I will only pass it on to this two vector if G is true, right? And this transform is like, I will pass it on to filter. I will pass on the result of invoking F to filter from whatever is passed to me. And iota is like, okay, I'm going to pass the numbers 1 through 5 to this thing that I'm wrapping. So we're wrapping the other direction, right? This is the fundamental difference between pull and push programming models. So this is pretty key, but I think if you're not getting it from this slide, you will get it as we continue going, because we're going to actually implement a push version of this exact pipeline. Okay? So let's sketch this out. I am going to do this in working code that we're going to write together. I'm trying to do it in the most logical order, but maybe not. Maybe you'll have to go back and replay this on YouTube and understand everything. But I'm doing my best here. And I will have a God bolt with all of the code at the very end that you can play around with. So let's get this, see if we can get this simple example working. We can definitely do better than this syntax-wise. We can get something very close to range of syntax if that's what we decide we want. But for the purposes of slide code, there's a few things I've added in here that make this a lot simpler. And we're not going to bother with the pipe syntax. We're going to use this operator instead. We are going to call and evaluate, so we don't have to figure out how to like have this whole pipeline cast to V or to a vector or something like that, right? And do a few other things that will simplify things, but this is working code. This is working code. By the end of this talk, this will be working code. And we get the same output, right? This is a push-style pipeline that gives us the same output, uses the same terminology, uses vaguely the same mental model, right? Question, quick question. Why would we use operator arrow equals instead of operator bar? Somebody shut it out, it's one word. Close. Associativity, that's the word. Associativity. So when you have a bar syntax, right, the associativity rules of C++ compose this way, right? When you have this arrow equals and basically any of the arrow equals operators, they compose right to left. And so in order to get something that composes right to left, remember we were talking about wrapping in a different direction. The simplest way to get something that composes right to left is just to use a right associative operator. You can actually do this with pipes. I have a demo library that's associated with this talk that I'll share a link to at the end. It's not real code, but it is like, you know, does all of the perfect forwarding things that we're not going to do in these slides. That does this with pipes, and you can do it with pipes. All right. So let's implement this, right? This is what we're trying to do. We're trying to make this expression lead to a vector that we can print like this, right? So let's think about the expression filter. I'm going to say the words pipe here because this is kind of what it's doing, even though it's not a pipe operator, but like conceptually. If you really hate that, please go to the YouTube comments and engage with the video so I get a lot more views. So I'm going to call this pipe. If it bothers you, I'm really sorry. We actually need two different types here, right, to represent this part of the chain. If we're gonna compose this at compile time, we need something that this expression returns. And the thing that this expression returns has to have an overloaded pipe operator with whatever this expression returns, right? And then also, that pipe operator needs to return an entity, right? So there's two different types here. So that is like, you know, we need a representation of filter before it gets composed, and then we need a representation of filter after it composes with its next step, right? And I'm just realizing that I switched to filter pipe into transform instead of transform pipe into filter, but I think you get the idea here, right? So in other words, like we have one object that's the result here, and then the other one is like made from this object somehow, like hand wavy sense. I promised no more pseudocode. Sorry, this is the last thing. This is real code. We're back to real code, okay? So I'm going to structure it for the purposes of this talk. You could do it a couple of different ways, but I'm going to structure it this way, right? I'm going to have, for all of the links in our chain, and I'm just going to use the term links. There's probably a functional programming name for all of these things, but like I don't care about mathematical elitism. And if you do, fight me in the YouTube comments. Like I actually don't think it's helpful to our community, but that's another soapbox. So I'm calling them links. The only reason I'm calling them links is because I asked my boyfriend to name my support library for this, and he said, "How about daisy chains?" Which I think is yes. I'll show him the clip of everyone clapping for him, and that will he'll love that. So yeah, I'm calling them links because that's because I can. And so the filter link needs to be constructed with a predicate, and then we need some sort of adapter that can be constructed from the filter link once we know what it's wrapping, right? Once we know what the next link is. Once we return from this, we will have constructed an adapter, right? So we need a concept design. Another way of saying that is we need a convention. We need a convention for how we're going to push data down this chain, right? There's not a lot of reason to overthink this. You can refactor this later until you've gotten it out in the wild, and once it's out in the wild, then you can't do anything. But for the purposes of slides, we don't need to overthink this. Push value seems like a good enough name, right? All right, so this is the start, right? This is where we're starting. So let's write this, right? If we get notice we're wrapping things kind of in the same way as the standard library code we looked at earlier, right? So remember, the standard library code we looked at earlier was doing things with the underlying iterator. So we are going to have something like that here. So can anyone shout out the implementation of this function? Go for it. Yeah, if predicate of value is true, next.push value. Yeah. So, I mean, I think this is, I don't know, I'm not really that in touch with reality all the time, but I think this is pretty understandable code. And like not that different conceptually from what the standard library is doing with ranges, but it's backwards, right? Remember I said inside out? I think that's the easiest way to describe it. All right. So that's filter done. I mean, there's a few details that we need to add in, like the operator, but that's filter. How about transform? I have big code for all of the people who are going to complain about the code being too small after the talk. I have big code on a few of the slides. I tried my best, but not all of them I could get this big. I am not a JavaScript expert, by the way, so like, sorry. Transform. All right, so transform is going to take a function when we construct it, right? The outer object that interacts somehow with this pipe operator is going to take the transform function. And by the time we get to this inner thing, we're going to need just the function and the next link in the chain, which looks an awful lot like the standard library example from earlier, right? Can anyone implement this one? Shout it out. Just shout it out. Next.push function of value. Exactly, right? Like, not hard once you get your brain past all of the infrastructure around it, right? It's actually very powerful. All right, now let's write IOTA. I think we can probably do this also. IOTA is a generator. So we need a convention for how we're going to tell the outermost part of the chain to start generating values. Let's just call it generate and not overthink it again. A note for everyone in the YouTube comments who's going to be like, that's a coroutine thing. It's close enough to what coroutines do with generators that I don't mind the clash for the purposes of this talk. But we can talk about clashing nomenclature on Reddit or in the comments, and I'm happy to talk about that. I don't think it matters for this talk. So here is our IOTA, right? We can use the same structure, right? Because we are going to be wrapping something. We know that this structure is going to stay the same. We are going to have a begin and an end. number, we are going to have those numbers passed on to the adapter, and we're going to have a nested link. And this is also pretty straightforward. I need to speed up, so I'm going to not ask people to shout it out, but I think most people here could come up with this, given staring at it enough time, right? We could have done a for loop over an iota range if we wanted to. In fact, we could have generalized this to loop over any range, right? But also we could do a regular old undergrad C++ 98 for loop, right? And that's fine too. Excuse me. All right, last one of the links in the chain, and then we're going to start talking about how we stick them together. All right? This whole thing, by the way, is 70 lines. All of the code I'm showing you here that makes that expression work, 70 lines of what I think is relatively comprehensible code. I'll give the Godbolt link later. You can get your cameras ready, take a picture of it. Or the slides are on the Discord, and you can just go in there and find it. So two-vector is a little bit of a different thing also, right? Because it is a terminal to this chain. It's a last link in the chain, and it's always a last link in the chain. It's not pushing to anything else, right? So we can still use the push value convention for the thing upstream of us pushing to us, but we don't have a way to go to the next thing. We actually just need a way to get the output out. We need a way for evaluate to call get output so that it can actually send it to a return value or something. And so it becomes a little simpler, right? We don't need this adapter. We can even use the default constructor of whatever container we're wrapping. We're just gonna assume this container is a vector for now. Let's write this, right? Oh, I used the wrong variable name. This should be output. Sorry, apologize. Output.pushback value, right? Very straightforward. We're getting pushed a value to us, and we are pushing it on to the next thing. It's just that the next thing in this case is not a link in the chain. It's an output, right? We're going back to eager world. And we're being very explicit about the spot where we go back to eager world. That is, when we put something into a vector, we have now used memory. We are now making something substantial that's going to cost us, right? There's not a lot of reason to overthink the output customization point name. Let's just call it get output. I am, because I intended to actually show benchmarks of this library and then didn't get them into these slides, or this library that we're writing here. I am going to actually do perfect forwarding here. This is how you would perfect forward. If you don't understand that, don't worry about it. But definitely, if it interests you and that kind of complexity or genericness makes you feel powerful, then learn about this. I don't know. It makes me feel happy. But it's not the point, right? This is the point. This returning of the output, this is something else. The main point being here that we don't really want to copy the entire vector when we return it, right? And there's no RVO that's going to protect us, return value optimization that's going to protect us from this particular copy. And so we do have to do something like this. All right, a couple more things. Remember what we were trying to make work. We have this, so we've done iota, we've done transform, we've done filter, and we've done to. We have not done this operator, and we've not done evaluate. How many lines do you think we have left to write? Who had 10? All right, that's not bad. Somewhere around there. Let's write evaluate. It's 2 lines. I'm not going to ask people to shout it out because I have 11 minutes left and I actually want to get to the end and I actually want to be able to take questions. Remember that we have wrapped outermost around innermost. We are wrapping from left to right, unlike the ranges, which is wrapping from right to left, right? So the outermost object is going to be an instance of iota : adapter, right? And iota : adapter has a function on it called generate. Remember, we named it generate. And so this thing, chain, is going to be that instance that we can call generate on, right? and then get output, you can call here. Now there's a problem with this, right? Anyone want to point out the problem? Go for it. IOTA doesn't have get output. We will fix that in a couple slides. What about operator arrow arrow equals? I know that several people in this room looked at that first slide and said, I will understand some of this, but this is the part I will not understand. This is not as hard as it looks. This really is not as hard as it looks. We can make this work with a mix-in, right? And mix-ins in C++23 are way easier. Generally, you do still want to use CRTP. I think Klaus had a good talk explaining why that's the case. So you should go back and look at Klaus's talk from this year. But in this case, we don't quite need it. We can use deducing this from C++23. If you haven't heard of it, it's a fantastic feature. You can basically write Python in C++. So we can mix in this operator via inheritance. And this is not even a mixed-in friend. This is truly intrusive inheritance, which means we don't have to go scan the entire namespace. This is not a hidden friend. This is a member function operator : equals. And we are still able to get all of the various reference categories and all of the various constantness categories, qualifier categories, into this, right? There's a couple ways we could have done this. One is that we could have had our adapter layout be the same across all of the links. That would have been, and then we could have just like directly constructed : adapter here. I wanted to be a little simpler for slide purposes, and I just created an adapt function. Like that's our customization point that we're going to call on each of these links. And then we have adapt, right? We implement adapt, which is basically to just construct the adapter. We're just constructing the adapter from our member and moving out of the parameter because perfect forwarding on slides is a nightmare. But this is something you can do. If you take a parameter by value, you can always move out of it, right? Unless it doesn't have a move constructor, in which case I'm not sure how you took it by value. Is that allowed? Somebody can tell me if it's allowed. I think it might be. Also, we have to add a constructor now. Anyone want to know why we have to add a constructor if we want that syntax to work? So that aggregate construction doesn't have to use the base class. Exactly. All right, last thing. What about propagating get output? I would hope probably a third of the people in the room at least at this point could write this if you needed to, but we can use the mix-in again. So yeah, remember we had this chain and the outermost thing is an iota and we need to propagate it somehow. But we have this mix-in that does output pass-through. We can use C++23's stood forward like, which is either really great or completely irrelevant, depending on if you write way too much generic code. So stood forward like, and we want to forward the underlying, our next, right? Our underlying link, our next links dot output. And anything that it makes sense to forward back the output with would make sense here. We do want to perfect forward this. We want to be very careful with this because this is where we could end up with a lot of copies, right? And then we just inherit from it. So does this work? Have we fixed TPOIASI? How many times do people think we are going to see transform, and how many times do people think we're going to see filter? Hopefully 5, right? 5 of each. And in fact, we do. I have to scroll code again because I'm not very good with JavaScript. But yeah, we get exactly the same behavior, exactly the same output without the extra calls. Here's the God bolt. If you want to take a picture of it, or if you're on the Discord, you can go find the slides. They have a God bolt link in them. Yay, right? Like, this is great. I have 5 minutes left, so I'm going to go a little bit faster. Okay, how about take while? Let me jump in and do this really quickly. What about take while? We can write take while pretty easily too, right? We have this like is done variable that once it triggers, We don't want to keep pushing things forward, right? And so we check the predicate and update is done each time, right? And if it is done, then we don't want to keep checking the predicate. We just want to push nothing forward. But if not, we want to keep pushing the value forward, right? Pretty straightforward. What's wrong with this? Anyone want to say what's wrong with this? Yeah, you still have to evaluate the whole range before you, right? We need to update our convention a little bit, our concept, right? Our convention. We could return a push result here. And now all we have to do is keep returning through the chain, saying, oh, okay, return stop iteration. This probably should have been just true here, but whatever, it works. And now we've somehow propagated back the information that this particular link in the chain is done iterating, and we should not keep iterating. And then we go back to our iota, right? In our iota, we can say, if we get the stop iteration, break, right? I think this is code that, like, the parts that are inside generate and inside push value are something that I think you could reasonably assign to an undergrad student as a homework. I don't think that this part is complicated. It's just getting your brain past all of the infrastructure around it, which is hopefully not that complicated. I've actually played around with this a lot. I'm going to keep playing around with it in the next few weeks. But like, you can make similar extensions to make flatten work, to make zip work. Propagating type information is very hard. I will say that. If you've ever heard the expression before, type information only flows in one direction in C++. It's because we have a form of reflection in C++ that we've had for a while. It's decal type. It's the only form of reflection we've had in C++, but that works really well with pull-style models, right? Because information is flowing through the output types. In push-style models, how do you figure out what it's expecting, right? It's not very obvious. So type information is a little bit complicated. I have a demo library that does all of this. It is not quite done. Really quickly, I'm going to go over a tiny bit, but let's write reverse. What goes here? Anyone have any ideas? It doesn't work. There's just no way to do this. This algorithm fundamentally does not work with a push-style model, right? Which is actually kind of interesting because this was also the algorithm that was probably the simplest algorithm that was problematic in Nico's talk. So if you want to go back to Nico's talk and see where he ends up, I think there's probably some like mathematical connection between these two problems. But this doesn't work. Almost everything else in the standard library does work, albeit some of them a little bit awkward. So what have we learned about output iterator composition? So output iterator composition or output range composition is an inside-out version of SID ranges. Both push and pull models can be lazy. In fact, I would argue that our push model that we mess with here was lazier than the pull model in ranges, right? Push models can work around TPOIASI by merging the output iterator analogs of increment and dereference, right? Those customization points were both in one spot, right? Push value. And so that kind of way of slicing customization points tends to work better for this particular problem. That simply doesn't work for certain use cases. Reverse, we already said, there's just nowhere to even start, right? Sort or anything else that's multipass is very awkward. Slide can be done with like a buffer in the middle or something like that, but it's super awkward. You can also do things like return a go backwards token or something like that, but all of that starts to look really unnecessarily complicated and loses some of the advantages, right? There are also simply some things that don't work in a pull model. For instance, flat map. We have a version of flat map in the standard. I think it's called like, somebody help me out here. Flatten transform. I don't exactly know. Anyway, I could be wrong about that. If I'm wrong about that, YouTube comments. Go to the YouTube comments. We love YouTube comments. Anyway, flattened one-to-many transforms can be done. They're awkward because in a push model, right, you can just allow the user's lambda or user's predicate to push to the next layer multiple times within the same function. And they don't have to like return something and then kind of restore whatever they were thinking about each time, right? So there's some things that are more awkward in one way. There's some things that are more awkward in other ways. The nice thing about all of this is that push-style composition can exist alongside pull-style composition, which I think is actually really cool here, right? Like the thing that we took in at the beginning was a pull-style range composition, or could be a pull-style range composition, and then we can do push-style range composition off the end. We can stick the two models together in one spot. I actually also have a way to turn a pull-style into, to turn a push-style pipeline into a pull-style pipeline. Did not get time to put it into the talk, but it will be in the library that I'm gonna release alongside this. This is a good thing. This means that we could have both of these types of programming models alongside each other in the standard library one day. Maybe. It's a lot of work, right? But maybe. All right. I am 1 minute over, I'm sorry, but the library, proof of concept library I have called Daisy Chains expands on this talk. It is not done yet. I will promise to do my absolute best to have it in some working form by the time this talk goes up on YouTube. I'm also going to try streaming myself working on this library on Twitch over the next few weeks. I am currently in between jobs, and I've kind of always wanted to try this anyway. So if you want to watch, my plan is to begin Monday, Wednesday, Friday, starting in October, noon Pacific. Jump on and interact. I'll be working on the standard library things. I'll be working on this library. I'll be working on some random metaprogramming nonsense. We'll goof off, whatever. Follow me on my socials for updates. Here's my social media stuff. And thank you for bearing with me in the 2 minutes I went over. I will take questions for as long as production team will not kick me out. And once they kick me out, I'm sorry, I'll talk to you in the hallway. Go for it.
Thank you for the presentation. I just have a question. Why don't we change the definition of operator plus plus in the push model to just do nothing and record the number of times it's been called, so that when you dereference it?
In the pull model or the push model?
The pull model.
That is one direction we could go, I suppose. Yeah, you still need to be able to compare end. So you actually do need to be able to check that you've not run off the end.
Oh, yeah, thanks.
But like I said, there are probably other ways to do this within the pull model and to avoid TPOIASI. And I think that we should actually be exploring those in the standard.
All right,
I
thank
completely
you.
agree. Go ahead.
I had a similar comment. You could actually use star, the dereference, to do some of this logic in the pull. But the other question I have is, with this push model, what about the iterators? Like when somebody says begin, what would come back?
So yeah, I mean, an iterator is fundamentally a pull model abstraction, right? And so we need something that's analogous to that. The problem is in the standard library, the thing that we've had that's analogous to that is output iterators, which are really awkward to compose in this kind of model. So I think we need to really rethink what we're doing there, right? Output iterators are so awkward. The standard actually says, the standard acknowledges the fact that we really want one customization point, but we have two. And standard library algorithms are only allowed to call plus plus once per assignment, and it must call one assignment per plus plus. It's like basically saying in the standard, this should have been one customization point, but it's two. So I think we need to rethink that. I think we need to look at it very carefully in SG9, and I think we need to come up with some design that's going to work going forward and be sustainable.
Okay, thank you.
Hello. Thanks for the great talk. I'm a PhD for database systems. So what you demonstrated seems to me it's kind of the Volcano model with two different plan processing direction, like the top to bottom one and the bottom to top one. I'm wondering, because in database system we have other models. For example, the materialized model and the vectorization model. Basically, like the first one is to like always calculate all the values in the first layer.
Right.
Like,
Eager is what you're talking about.
Yeah. And the vectorized model is kind of a hybrid of them. I'm wondering, like, is there any like plan or proposal to support like all of them? Because like seems to me, because it's possible to have one like plan with different model of execution, right? So in theory, it should be doable for like all these three type of execution model and like with both push and pull based direction.
Yeah, I mean, I think there is some work in that direction. I think there's a proposal in flight right now for parallel ranges. It's complicated. I will say that the standards committee in general has not been super interested in eager models. I do think that's a little bit of a mistake. I think we should be addressing people who are used to eager models. The reason why we haven't is that we are so focused on zero overhead and delivering zero overhead that if we come up with so many scenarios where the lazy model is more efficient than the eager model, that no one wants to be the one who says, this overhead is okay for the understandability of the code. So I'm going to go over here, and then I'm going to get David, and then we'll end.
Great talk. I'm wondering if you've given any thought to whether the daisy chains perspective is applicable to the sender receiver model that also has a composition.
I hope someone would ask that.
And if so, what are your thoughts?
Eric and I talked about this way back in 2018. When I first implemented sender receiver, when he first showed it to me, I was doing receiver composition and he was doing sender composition. So we had the exact same problem. Sender composition works a lot better with coroutines. That's the biggest problem here, right? I have not re-explored that since 2018. The coroutines argument was enough to get me to jump on board to sender composition. But I think there's something there. There's something to be explored there.
I think saying that it's receiver composition is a beautiful insight. So
thank you.
Thanks for the talk. My impression of ranges and kind of like these examples that you're showing me is that it's quite complicated and unexpected from a new user standpoint, the kind of behavior that you get. And I really quick tried your example of the map transform in Rust to see what its behavior was. And it did the expected thing. There was no weirdness to it. And I wonder, should we not try to focus on ergonomics more in C++ in our library development and our APIs so that we don't get these corner cases, even if we sacrifice some particular niche way of using the library?
Yeah, so this is an interesting question, right? Rust does get this correct. I think that we don't have the ability to evolve quickly enough, and I think we need to figure that out. I don't think that throwing out lazy altogether is going to solve this problem, right? Like, I think having an eager model would be nice. But yeah, I do think we need to have something in the standard library that does the expected thing here. I think one route to that, with all of the backwards compatibility that we have to explore or support here, is to build up a hierarchy of output range adapters. And I think that that's something that I do want to try and explore in SG9 in the 29 or 32 cycle. So yeah, thank you. I will be happy to take more. I'm getting angry looks from a volunteer though, so I will, no, okay, I can take one or two more questions. One more question, I can take one more question.
Okay, a very naive question. Okay, you have this implementation of filter iterator that needs to dereference the same thing twice. Why just not the cache, the last value, and then you use it when you, what would that break? Yeah,
so I mean, there's a couple of reasons why that could be very bad, right? If the last value you got is a reference, and then you could dangle that reference, right? That's one thing that can go wrong. Another thing is that if you have filter composed with filter composed with filter composed with filter, you're ending up having to have that storage over and over and over again on the stack, right? And caching that storage, that adds up, right? Your stack size is going to grow quadratically or cubically, depending on how it's implemented. But yeah, sticking that storage in the object representation has a cost.
Thank you.
Thank you everyone for coming. Thank you everyone for everything this week. I really appreciate you all. This CppCon and C++ community is such a great family, and I really appreciate everyone that's helped me through this week.